All right, I'm gonna try to speed through this. I'm realizing 15 minutes isn't all that long, so I'm gonna be accelerating American style options. If you want to take a look at the paper there, and here's the abstract. You can pause and take a look if you're interested. Um, so we're gonna be talking about accelerating American style options. So first, what are options? So options are a contract between two parties. We're going to keep things simple, and we're only going to consider one side of it, which is the person who gets the right to either buy or sell. In the case of the right to buy, it's called a call option. And in the case of the right to sell, it's called a put option. So here you can see some like fake stock price on the left. And then there are three variables there. There's K, T naught, and Tn. So T naught and Tn define T naught is like the current time. And then Tn is the end of the contract because it's just an agreement between two people. There's a finite bound on the amount of time that it's live. Then K is the strike price. It's the price at which you agree to either buy or sell, or to buy it at or sell it at when you decide to execute your right. So on the top right there, you have the simulated call value of the asset price on the left. So as you can see, we only care about um, the asset when it's above the strike price. To give you some intuition there, it's kind of like a Black Friday sale, where you're going in and you're buying something for less than you otherwise would be able to get it at. So essentially, you're getting something that's more valuable at a lower cost. Because here, when say we pick the peak of the call value in that top right graph, I'm able to buy something at price K when it's actually worth K plus N, where N is some positive number. So at that point, I was able to get like a deal, right? And that's awesome. Then there's kind of the reverse on the put, but since we're short for time, I'm going to skip that. Um, so those were like the two broad buckets, but then there are different like styles or types. Um, because at the end of the day, it's a contract that you can get pretty creative. So in the basic case where you use the Black-Scholes, um, it's called a European option, where you can only exercise your right at the end of the contract. So in this case, TN. So in our fictitious example here, um, although it was valuable at some point, our call option, at the time that it expires, it's worthless. So womp womp. Um, and then to kind of counteract that problem that I just described, so someone came up with American style options where you're able to execute at any point between T naught and TN. So unfortunately, that makes things a little bit more complicated because you have a bunch of decisions to make and you're trying to find the optimal one. So that's where the kind of the inspiration for the project came, and the paper that I found, because they wanted to try to speed up something which is otherwise sequential. And I'll describe why it's sequential shortly. And then the swing option is it comes from baseball, taking a swing. You get multiple at bats, so you're able to exercise multiple times. But so it's essentially just an extension of American style options. Um, so yeah, so essentially, our goal here is to calculate the expected value of our option given optimal behavior. So the optimal behavior bit is just an assumption that we choose to make. Obviously, I don't know if people are able to behave optimally all the time, but in a perfect world, that's what we're working with. So we're going to assume that. So it's a really simple arbitrage. What we want to know is my expected value, essentially the future value in the average case, higher than what I can get right now for it. If it's higher, then I want to hold, right? Because if I wait a little bit longer, then it'll be worth more. And then in the reverse case, where the current value is higher, then if I hold it, it's only going to go down in value. So obviously, I want to exercise my right now. So if it's more valuable in the future, I want to hold it. If it's less valuable, I want to exercise my right now. So our goal is just to figure out what that expected value is, which is complicated because we have to like predict the future. We have to be in the present and try to figure out what the future is going to bring. So the traditional approach is the least square Monte Carlo method, brought to us by Longstaff Schwartz paper, their paper. Here's a little bit of math. I don't expect you to pick that up. It took me a long while to figure that out. So I'm just going to give you the intuition. So Monte Carlo simulations in general uses just a bunch of like random guesses to try to come up with a distribution of the possible outcomes. So to be a little bit more clear, in our case, what we do is we have this Monte Carlo simulation and we want to inject some assumptions because it itself doesn't know anything about current market conditions or the asset. So we have to learn those kind of assumptions. That's commonly done with like data analysis and stuff. We didn't worry about that here, but essentially you make some assumptions about the market. So it's able to kind of predict possible futures. And then you run just a bunch of them to kind of leverage statistics to try to get to a reasonable approximation. So we're going to guess a bunch of random futures with those underlying assumptions about the market. And then for each of those paths, we're going to kind of walk ourselves from Tn to T0 because at Tn, our decision is easy. There's no future to consider. Anytime after Tn, it's worthless. So whatever our decision is, it depends on whether it's a call or a put. So I'm just going to keep it generic. Whatever our decision is, it's clear. And then once we know that a clear decision on Tn, we're able to go to Tn minus 1. And we're able to compare our current to the value in the future. And then we'll just pick the best one of those and then go to Tn minus 2 and then compare the current to the future and so on and so forth. You see, this is the sequential bit that I was talking about, how every current decision relies on the future. So you need to kind of walk back from the future to the present. And because it's a finite bound on the contract, we're able to do that here. So hopefully that's at least semi-clear. And the motivation is this is the world of finance. It's cutthroat and it's really fast. So we need to know exactly what's going on as soon as possible so we can make the best decisions we can. And we have this sequential problem, which sucks for parallelization. So otherwise our hands would be tied. So the authors of the paper came up with this parallel optimized approach where you use tree quantization. So quantization in general is being a little bit more relaxed about precision in hopes of simplifying things enough where we can speed things up. So to give you the intuition, again, you could pause on the last slide if you're interested. I recommend the paper if you want to get the whole picture. But anyways, so essentially what we're going to do is we're going to use Vinori partition. So essentially we're going to create this grid of possible outcomes. In this case, it looks like a tree on the left. And we're going to just try to, for each simulated price in our Monte Carlo, for each time period, we're going to have this like bucket, which is what these columns are. You get these like, there's 1 on the far left, and then 2, and then 3, and then 4. Those are like the buckets, the possible, like the discrete outcomes. And then all we're going to do is for each of those simulated prices, we're going to try to figure out at each time period, what's my current price closest to in this grid. And then that's going to essentially give us like a count for each of these nodes. And then we're just going to use these counts to come up with probabilities of going from the previous time to the next time. So you can imagine going back to our graph there. We have this tree, and then we're going to use the Monte Carlo simulation to approximate the probability of going from one level to the next. And that's important because that gets rid of the sequential nature, because there's no kind of backtracking anymore, because we're able to immediately use the probabilities. Given some state, I know the probability of going to the next state. So that's the motivation. That's kind of the high level. We're going to be using probabilities instead of this like dynamic programming backtracking kind of thing. So in terms of the implementation, I chose to go with 4 different algorithms. I went with the naive CPU only. Then I went with a partially accelerated least square Monte Carlo. So although we spoke about like specific paths, you're able to group all of the paths into a matrix and do matrix operations. So I tried to accelerate the matrix operations with the GPU, although there was still that sequential nature. Then there were two quantization, tree quantization algorithms I approached. One was pathwise and the other was timewise. We'll see some pseudocode later. So yeah, those were the kind of four big approaches that I went for. So on the left, you can see that is that is the pathwise algorithm. M is the number of paths, and n or like in the second loop there where k is equal to n is the number of time periods. So on the outer loop on the left, we worry about pathwise, and then on the right, we worry about timewise. The strategy here is just to make the data more optimally placed for coalescing. So when we do memory operations, it is able to ideally perform better. Although we'll see shortly that it actually didn't. That there was a distinction in the paper between the performance of the two algorithms, but I suspect because well, I'll get into it shortly. So the results of these four algorithms are as seen. So the paper for some reason decided to talk about it in time as opposed to performance like gigaflops. So we're just gonna do that so we can kind of compare an apples to apples. Um, so as you can see here, we have the CPU in yellow, the CPU only in yellow, the partially accelerated in green, and then the two quantization trees in blue and red. See how they're kind of on top of each other. That's what I was referencing before. I have a theory that in the paper I wasn't able. There was no code to see. If you look at the paper, it's all math, and then there's some pseudocode which we saw previously. But I have a feeling that they used the essentially there was this like big three-dimensional matrix that I had to use in order to remember all of these like probabilities and stuff. And I changed the shape of the well, it was still three dimensions, but the dimensions were the number of paths, then the number of like grid points or options in each time period by the time period, the number of time periods. So I rearranged it to try to make it more optimal in terms of memory coalescing, depending for quantization 2 and quantization 3. And I have a feeling they didn't do that in the paper, which is why when you adjusted that those operations are the most memory intensive. So by like tweaking it a little bit, you were able to optimize it so that there was less of a distinction between the two. But that's just a theory because I can't confirm it since I don't have access to their actual code. But as you can see, our GPU accelerated ones perform worse on small ones and perform better on large inputs, which is good to see. It's reassuring. Because ultimately that's what we kind of expect, right? The CPU kills it on really small things, and then the GPU steps in and is able to overcome the CPU with its massive throughput on these larger operations. And then here you can kind of see what I was talking about before, how they're just really neck and neck. Sometimes one's higher, sometimes the other's higher. I really think that was just due to the rearranging of that like really enormous 3D matrix tensor. But yeah, beyond that, I'm not entirely sure why my implementation was able to or the two of those implementations were so close to each other. But it looks like we're out of time. I think I'm at 15 minutes, so there's the link to the paper. And hopefully you learned a little bit something about options or GPUs, ideally. But yeah, it was a cool project, and I'm it took a lot of work, but it was fun. So thank you for your time, and Enjoy it.